In this module, we will actually try to talk about and discuss how a typical network is actually structured. So, how will the structure of a network will look like. So, when you look at the network structure, we need to identify that there are typically different parts of a network structure. So, I have something called as a network edge. So, the network edge will be the systems, the network edge will be comprised of systems that is actually running my applications, and where the applications are going to run, the applications are going to be actually running on my host systems. So, the host or end system, as we were referring to in one of the previous modules, are the systems on which I will typically be running my network application. So, be it a browser application or web server application, be it a file server or be it a email client or an email server, whatever it is. Now, the next part of it is basically the network core. So, the network core is basically going to be consisting of typically this part of my entire network, and here I will typically have routers and switches devices configured and running. So, as we were discussing in the previous module, the router devices is going to be the device that is actually responsible for forwarding the packets from a given source to a given destination. So, if I have to have my packets reaching to a network which is actually 10 hops away, right, the router device is the device that is responsible for that. So, in networking world, when we say hop, we typically refer to one router device to another router device. So, when my packet is going to go from first router to the second router, technically it is referred to as one hop, that the packet is actually taking in its path towards the final destination. So, the network core part of it is going to be consisting of router devices which has this responsibility of forwarding the packets from the source to reach the final destination after taking many hops, right. So, how many hops it takes will be typically dependent on what is the source and where is the destination and how many devices it has to cross to reach the final destination, right. So, between the network edge and the network core, you have typically the access networks of the physical media. So, which are the communication links at the physical level that is going to be actually transferring the data in bits, right. So, that is where we really talked about the transmission rate or the bandwidth, and the parameter of the transmission rate is basically what is going to differentiate between the different communication links, and what communication link we will typically try to make use of will be dependent on what is the type of data that I am trying to transfer and which my network application is dealing with. So, if I, for example, are using I am dealing with a network application that is dealing with voice kind of traffic, then I would not want too much of a latency associated with the transfer of the data from the source towards the destination, and because of this reason I would go in for very low latency, less fault available, less fault inducing link, as compared to let us say I am actually dealing with an application where I am transmitting the normal data across from one machine to another machine, where I would not be bothered too much about a small amount of latency being there, and likewise based on the type of data that my application is going to be transferring from one system to another system and my own business requirements, the organizations will typically will decide on what kind of communication link bandwidth that they will typically want to make use of. So, the end systems which is basically comprising my network edge is going to run the application program. So, as I was just explaining, the application program here could be a web program or an email program, and they will be typically at the edge of the network. So, why do we call this as the edge of the network? Because if I consider this entire thing as my network topology, you will typically find the host, the end systems actually running only at my edge of my entire network topology. So, whether it being a client or whether it being a server, you will always find that these are typically at the edge of my network and not right in the middle of my network, right. So, that is the reason why this part of my network is actually referred to as a network edge. So, network edge typically consists of host or end systems in which I run my network application. So, whether it be a client application or whether it be a server application. So, in the client server model, how do we differentiate between a client and a server? Now, a client end system is typically an end system that is actually will initiate the request, and to whom will it initiate a request? It will initiate a request to a server that is actually running on some part of my network, and the server is always expected to be on, because unless and until the server is on, the client is not able to be successful in communicating to the server all along. So, the server is expected to be first brought up, it should be available, it should be waiting for acceptance, waiting for connection request coming in from any kind of a client machine on the network, and when it comes in, it basically accepts the connection request and then sorts of does the service whatever the client wants it to do, and then sends a packet, response packet back all the way to the client, right. So, that is basically what we refer to as a client server model. So, it could typically be a browser, a web browser like your Firefox or your Chrome or your Internet Explorer browser talking to a web server like an Apache server or an IIS server or a Tomcat, whatever it is, and trying to get the data from there and then displaying it on your browser window. Or another example of an application could be an email client application that I am running here, and that client application could be trying to talk to the email server application that is running on my network and trying to get the data back, right. So, likewise there are so many different combinations of the client and servers that are possible, and also which we are using on a day to day basis in today's highly networked world. On the other hand, I could also have something called as a peer to peer model, where I do not really have any specific server classified as a server and another machine classified typically as a client, and it always will be dependent on the need basis, where any system on the network could actually start acting as a server and another system can be acting as a client, right. So, some examples are something like Skype. So, when we talk of a connection oriented service in a network edge point of view, what we exactly mean by connection oriented service is that the basic purpose is that the data transfer between the two end systems should be done after there is something called as a handshaking that is done. So, what exactly is handshaking? So, the handshaking is basically a set of steps that will be executed for doing the initial setup between the two end systems that wants to communicate, right. So, it is like a sort of the sequence that we typically have whenever we try to make a phone call to our friend or to whoever it is, wherein initially there is an exchange of an hello hello on either side, right. So, if you see retrospectively, why we use the word hello is to ensure that we are able to hear what the other person is speaking, and similarly the other person is able to hear what we are speaking. Likewise, in the computer networking world, when I am basically trying to set up a connection oriented service, there is an initial set of steps that is actually done, which is technically referred to as handshaking between the two end systems, wherein both sides sort of agree upon the other party's capabilities and limitations, so that the data transfer, when it happens at the end of this handshaking phase, could be very effective and also it could be very reliable, right. So, it sorts of sets up the state in the two communicating hosts, that is basically the two end systems on either side of the network that is now trying to set up the communication path, right. So, what is the protocol that is actually used for this? That is nothing but TCP. TCP stands for the transmission control protocol, and this is actually one of the very popular protocols on the internet today, wherever there is a requirement that the data requires to be reliably transferred across to the other side. the application developers will always use TCP as the underlying transport mechanism for transferring the data across. So, what exactly are the different services that the TCP provides, the TCP protocol provides for the end systems? It provides a reliable in order byte stream data transfer. So, what do I mean by reliable here is that if I am basically transferring 10 bytes from my client to the server, all the 10 bytes has to be delivered to the server, right. That is basically what we are meaning by reliable. Now, what do we mean by in order byte stream? If I am transferring the data, let us say as NPTEL, right. The in order delivery essentially means that the server application should be receiving the data in the same order. So, it should be receiving it as NPTEL. So, NPTEL, it should be receiving it in the same order and it should not be in a jumbled up order, right. So, that is basically what we mean by reliable in order byte stream data transfer. So, how do we actually do this reliable in order byte stream data transfer in TCP is that we actually try to make use of an acknowledgement and a retransmission to detect if there is a loss, and if there is a loss, the sender will sort of retransmit the data till it gets acknowledgement from the other side, yes, that I have received this particular data. So, the second service is basically what is called as a flow control. Now, what we mean by flow control is that let us take an analogy of a normal human conversation between two persons. Now, when we are actually having these two people talk face to face, there are always indications given by one party to the other party of whenever there is an overflow or whenever there is an too much of information that is being provided, the other person can say that please give me some time to assimilate whatever you have actually just now told me, right. So, what this other person is communicating thereby is that I need some time to digest the information that you have given me, and therefore, please stop communicating henceforth till I tell you to restart again, right. Now, similarly, in the networking world, when two end systems are trying to talk to each other, you need to have a mechanism by which the other party, the other end system could communicate to the other party that he has only limited buffer and he does not want to overflow that buffer if the data continues to keep coming in the same manner, right. So, that is basically what we are referring to as a flow control here. Essentially, the sender does not want to overwhelm the receiver by giving too much of data to it and thereby having the data overflowed on the receiver side, because it does not have enough memory buffer space to take charge of the data and then deliver it to the higher level application. So, how does the two end systems, that is the client and the server, typical, right. In a typical network you have a client and you have a server, how the two end systems communicate with each other, saying that I have only this much of space available free in my memory buffer for receiving more data from you. This entire process is basically what is referred to as a flow control. So, in the flow control, we are essentially trying to ensure that one side does not overwhelm the other side and sort of overflow the data which is received on the receiver side, right. And so that the flow of data between the two end systems is controlled in this manner as part of the reliable service that the TCP protocol is actually offering to the applications. Now, the next service is basically the congestion control. Now, the flow control that we talked of recently is sort of trying to deduce the capacity of the other end system at any point in time, so as to ensure that the buffers that are there at other end systems are not overflowing. Now, this takes care of the limitations or the capacity that I have on the two end systems at that point in time, but I also have a requirement that the data that is getting transferred from the source to the destination, which is actually going to go over a network across multiple hops as we just saw, is also, the network is also capable of sort of holding the data without the data getting lost in between in some of the devices that the data is going to cross. So, like as I was giving an example before, if my data is actually going to go from one device in Chennai to another device in Mumbai, it has to possibly cross, let us say, like 6 different devices for example, right. I have to ensure that on all the 6 devices there will be sufficient memory buffer space available, so that my data that is actually passing on all those 6 devices could be using that memory buffer till the time that it is able to get successfully transmitted out of that device into the next device on the path. Now, how does this get ensured is by the mechanism called as congestion control. So, when I say congestion control, what we essentially try to find out is we use some intelligent mechanisms to detect whether the network is it getting congested, and whenever there is a detection that the network is getting congested, I am going to sort of slow down the amount of traffic that I am injecting into the network as a client system or as a server system, so that over a period of time after I slow down my injection, the whole network starts off getting free, and once I detect the network is getting free, I am going to start increasing the rate of traffic that I am going to inject into the system, right. So, likewise I basically have a mechanism by which I detect the state of the network at any point in time and do a sort of a self adjustment depending on the state of the system. Either I try to induce more traffic or I try to reduce the amount of traffic which I am injecting into the system, right. So, that is basically what is referred to as a congestion control. So, the TCP service basically offers a reliable in order byte stream. It ensures flow control so that the data is not lost because of lack of sufficient memory buffers on my end systems. It does congestion control to ensure that the data is not lost because of lack of memory buffers on all the intermediate network devices like my router devices not having enough memory buffer space at that instant of time. So, with respect to the connectionless service, the data transfer, again the objective is to basically do the data transfer between end systems, but here I do not have an explicit connection setup like I have in the connection oriented service, and the most commonly used protocol in the transport layer for providing connectionless service is basically what is referred to as UDP protocol, user datagram protocol. So, it is basically a connectionless service, there is no explicit connection that is created before I start doing the data transfer. It is an unreliable data transfer, there is no flow control or no congestion control that is actually done in UDP. Now, some of the applications that I actually use TCP is HTTP, that is typically your web based protocol. So, HTTP, HTTPS and so on. FTP, that is your file transfer protocol, Telnet, your SSH, your SMTP, all are different applications which will typically require to run over the network. These kind of applications will typically try to use TCP. The applications which actually use UDP are applications like my streaming media, so DNS, my network management, that is SNMP related applications, any kind of voice related applications, all these applications make use of UDP as my underlying transport protocol. Thank you.